Hi, Stu Schwartz from MasterMathMentor.com. This is video BC27. The topic is first order differential equations, and it covers the BC manual pages 179 and 180. In AB and BC calculus, in order to solve differential equations, they had to be separable. That is, they had to be in the form of dy dx is equal to f of x over g of y, or g of y dy equals f of x dx. All the y's on one side, all the x's on the other. If the differential equation could not be put in that form, we could not solve it exactly. If we had an initial condition, we could approximate a solution using a slope field or Euler's method. Differential equations is a college course in of itself, but here is a sampling from that course. A first order differential equation is in the form of dy dx plus p of x times y is equal to q of x, and we will look at the technique to solve these equations. Here are four examples of first order differential equations. All can be put in that correct form. dy dx equals x plus y. dy dx equals x squared minus y minus 1. dy dx is equal to 4y minus sine of x. dy dx equals y tangent of x plus sine of x. Notice that all of these involve sums or differences of expressions with x's and y's, and that is why they are not separable, but they can be solved with the techniques that we will look at for first order differential equations. Here are the steps to solve a first order differential equation. First, we need to get the DEQ in the proper form. The four examples shown at the left are not in that form, but it is certainly easy enough to put it in the correct form. We then need to identify our p of x and our q of x. We then integrate p of x dx, and then create what is called the integrating factor, mu of x, which is equal to e to the integral of p of x d of x. Our general solution to the DEQ is simply y equals 1 over mu of x times the expression, the integral of q of x, mu of x dx plus c. Note that the c is inside the brackets and will ultimately be multiplied by 1 over mu of x. Let us first attempt to solve the differential equation dy dx equals x minus y. It is clear that this is not a separable differential equation. So let us see whether we can use our technique, which I showed on the screen, to solve this as a first order differential equation. The first step is to put it in the correct form. dy dx plus p of x times y is equal to q of x. And doing that, we get dy dx plus y is equal to x. That makes p of x equal to 1 and q of x is equal to x. We then combine the next two steps and say that mu of x is equal to e to the integral of 1 dx. The integral of 1 dx is x, and therefore mu of x is equal to e to the x. So we are now ready for our general solution. Y is equal to 1 over e to the x times the integral of x e to the x dx. To perform this integral, we will use integration by parts. U is equal to x, dv is equal to e to the x dx. Therefore, du equals dx and v equals e to the x. And therefore, this integral is x e to the x minus the integral of e to the x, which is e to the x plus c. Note again that the c is inside the bracket. So therefore, when we distribute the 1 over e to the x, we end up getting y is equal to c e to the negative x plus x minus 1. That is the solution to our differential equation, and it is a general solution because of the constant c. Let us check our work. Since y equals c e to the negative x plus x minus 1, c e to the negative x is equal to y minus x plus 1. If we take dy dx, we get negative c e to the negative x plus 1. And since c e to the negative x is equal to y minus x plus 1, dy dx is equal to negative quantity y minus x plus 1, which is x minus y. As a further verification, here is the slope field for dy dx equals x minus y. We show three specific solutions. The red at c is equal to 2, the green at c equals negative 3, and the black at c equals 0. And if c equals 0, then our solution is just the line y equals x minus 1. Problem 2 reads dy dx equals e to the 2x plus y. Again, it is clear that this is not separable. We first put the DEQ into the correct form. Dy dx minus y equals e to the 2x. That makes p of x equal to negative 1 and q of x equals e to the 2x. Therefore, mu of x is equal to e raised to the integral of negative 1 dx, and that becomes e to the negative x. So our solution is y equals 1 over e to the negative x times the integral of e to the negative x, e to the 2x dx. And this simplifies nicely to give e to the x integral of e to the x dx. Therefore, y is equal to e to the x times e to the x plus c, or y is equal to e to the 2x plus c e to the x. To check our work, first we move some terms around in our solution, and we get c e to the x equals y minus e to the 2x. Taking the derivative of our solution, we get dy dx equals 2 e to the 2x plus c e to the x. But we just said that c e to the x is y minus e to the 2x. Therefore, dy dx is equal to 2 e to the 2x plus y minus e to the 2x, and therefore dy dx is equal to e to the 2x plus y. Finally, we show the slope field for dy dx is equal to e to the 2x plus y, and we show three possible solutions for our equation y equals e to the 2x plus c e to the x. We show the red curve when c is equal to 5, the black curve when c equals negative 2, and the green curve when c is equal to negative 4. In number 3, you're given the first order differential equation, x dy dx is equal to x squared minus 4y. We'd like to find first the general solution and then the particular solutions given that y of 1 is equal to 1 and then y of 1 is equal to 0. It is clear that this is not a separable differential equation. So we put it in the correct form and get dy dx plus 4 over x times y is equal to x. That means that p of x is equal to 4 over x and q of x is equal to x. Therefore, mu of x is equal to e raised to the integral of 4 over x dx, which is e raised to the 4 natural log of x, and that is simply x to the 4th. So our solution is y is equal to 1 over x to the 4th, the integral of x times x to the 4th dx. And that gives 1 over x to the 4th, integral of x to the 5th dx, or 1 over x to the 4th times x to the 6th over 6 plus c. And expanding, this becomes x squared over 6 plus c over x to the 4th. That is our general solution. For our particular solution, we first start off with the point 1, 1, shown in red. We use the fact that 1 is equal to 1, 6 plus c, making c equal to 5, 6. So our particular solution passing through 1, 1 is y is equal to x squared over 6 plus 5 over 6x to the 4th. For the point negative 1, 0, in green, we show that 0 is equal to 1, 6 plus c, making c equal to negative 1, 6, and therefore y is equal to x squared over 6 minus 1 over 6x to the 4th. This is all confirmed by our slope field shown on the left side of the screen. In number 4, we would like to solve the differential equation x dy dx plus 3y is equal to sine of x over x squared. We'd like to find the general solution and then the particular solutions given the fact that y of pi over 2 is equal to 8 or y of negative pi is equal to 0. The DEQ is certainly not separable, so we put it into the correct form. dy dx plus 3 over x times y is equal to sine of x over x cubed, making p of x equal to 3 over x and q of x is equal to sine of x over x cubed. So mu of x is equal to e raised to the integral of 3 over x dx, which is e raised to the 3 natural log of x, or x cubed. So our general solution is y is equal to 1 over x cubed integral of x cubed times sine of x over x cubed dx. The x cubes cancel and we're left with y is equal to 1 over x cubed, the integral of sine of x dx. An easy integral to take, and our general solution is y is equal to 1 over x cubed times the quantity c minus cosine of x. For our particular solution, we first use the fact that y of pi over 2 is equal to 8, meaning that the curve passes through the point pi over 2, 8, shown in red. Therefore, 8 is equal to 8 over pi cubed c, and c is equal to pi cubed. So our particular solution is y is equal to 1 over x cubed times the quantity pi cubed minus cosine of x. For the second point, y of negative pi is equal to 0, meaning that the curve passes through the point negative pi 0, we get 0 is equal to 1 over negative pi cubed times the quantity c plus 1, meaning that c is equal to negative 1. So our curve is y is equal to 1 over x cubed times the quantity negative 1 minus cosine of x. Our solutions are shown on the slope field on the left side of the screen.